Welcome everyone to our second geology topic, plate tectonics. This is pretty much the fundamental concept surrounding all of what we see out in our world here and on the Earth. Plate tectonics originated with an idea of continental drift presented by Alfred Wegener. We'll talk about the evidence that surrounds plate tectonics and how it was basically brought into a theory. And then we'll look specifically at the different plate boundaries, which is where all the geological action takes place on the Earth's surface, and including hot spots as well. So let's begin today. Earth's layers can be viewed in two different ways, either by physical properties or chemical composition. We'll discuss both here. As you can see, there are standard differences. Chemical composition is kind of more of a simple breakdown, whereas the physical properties, things like liquid versus solid, partially molten versus solid, or gaseous, that's all different many different layers there. So we'll look first at chemical composition, then the physical properties. If we look at the layers of the Earth by chemical composition, starting at the surface, we have the low-density silicate crust, which has a variable thickness and composition. Generally, though, low density, the continental crust can be anywhere from 10 to 70 kilometers thick, and the ocean crust anywhere from 8 to 10 kilometers thick. A little bit thinner, a little bit more dense. It sinks down into the mantle a little more, producing low places on Earth, and eventually that's where the water collects, aka the oceans. This is why it's called oceanic crust. There is differences between the two. The mantle is made of a high-density rock called peridotite. It's very high in iron and magnesium, low in silica, but it's still a rock. The mantle is actually, it is rock. It's not kind of magma all the way down there. It is rock. It's superheated, though, but not rock nonetheless. The upper part of the mantle is actually a part that is very interesting, and we'll look at that in the sublayer. The asthenosphere is the upper part of the mantle that's actually kind of so heated that it's partially molten and produces a slippery surface for the excuse me, the lithospheric plates to ride atop. The core of the Earth then is made mostly of iron and nickel. The two layers broken up by physical properties that make up the surface of the Earth are called the lithosphere and the asthenosphere, the lithosphere being the uppermost layer. This is the rigid part of the crust in the upper mantle. It's about 100 kilometers thick, and it's usually pretty brittle. It fractures easily. It's kind of low temperature, so this is where most of our earthquakes come from, is movement from the lithosphere. There is a solid rock layer below the lithosphere, but that rock is so superheated and under so much pressure that it actually moves quite a bit. It's very ductile or malleable, as you would, and it's called the asthenosphere. This is a flexible part of the upper mantle that the lithosphere rides atop, and these are our two most important layers to really understand plate tectonics, which we'll talk about next time. The structure of the Earth by physical properties as you get below the two upper layers is first the lower mantle, about 2,500 kilometers thick. It's solid rock, but it's really superheated, just like the asthenosphere, under pressure, still capable of quote-unquote flowing. The outer core is the next layer. It's liquid iron and nickel. It's so hot down there, 2,250 kilometers thick. It's so hot down there that it maintains its liquid form. But once you get into the inner core, a radius of 1,230 kilometers, it's solid iron and nickel, and it's because of the fact that there's so much pressure that it maintains its solid form. It's thought that because the hot liquid outer core of the Earth spins rapidly because of the Earth's rotation, that a magnetic field is formed around the Earth. It causes a magnetic dynamo. Any planet really that has a liquid metallic layer and rapid rotation is going to produce a magnetic field according to the magnetic dynamo effect. Here's a look at the structure of the Earth one last time to review, especially those upper layers, because they're going to be most important when we talk about plate tectonics. We see here the ocean crust in the upper left, the continental crust in the upper right. There's kind of a little boundary or a difference in the rock between the crust and the mantle. That's called the Mohorovicic discontinuity. That's the boundary between the kind of the crust and the mantle. But there is a rigid part of the upper mantle, and the rigid part of the upper mantle plus the crust forms the lithosphere. And so you can see that's why there's kind of a bracket there indicating that the lithosphere is a thick layer there. Underneath that is a asthenosphere. It's a hot layer. That rock is kind of quote unquote flowing or mobile, and then you have the lower mantle. We begin with continental drift. In order to understand continental drift, first we kind of need to understand just the overall idea of the theory of plate tectonics. The Earth's surface is made up of a series of lithospheric plates. We talked last time about lithosphere. That's the crust and the solid part of the upper mantle. These rock slabs slide around on top of a partially molten asthenosphere. This is the idea of plate tectonics. Now remember, a theory is an explanation of a set of observable natural phenomena, which we would refer to as laws. Now we actually have lots of observable natural phenomena that come together to form this theory of plate tectonics, so we're going to talk all about that today. But just keep in mind that a theory is an explanation. In 1915, Alfred Wegener proposed his idea of continental drift, that all the continents had once existed together as a supercontinent called Pangaea, and they had been drifting apart for the past 200 million years to make their current positions and appearance today. Plate tectonics seemed like a good idea, and Alfred Wegener did a great job at gathering lots of evidence to suggest this was the case, but he really could not explain how the continents were moving, which is why it was rejected as a theory, but more of just a kind of hypothesis or start of a theory. With continental drift, basically Alfred Wegener saw that the continents fit together like puzzle pieces, that the rock layers along the coastlines where the puzzle pieces would have matched up kind of line up with one another. The fossils present on the different lands would not have been able to exist independently of one another, but had to have existed when the lands were once together. And the climate evidence suggests that the continents were all put together at one point. So let's take a look at how this all works. You can see that it's intuitive that the continents do fit together like puzzle pieces. Also then, if you compare the rocks on both sides of the continents of Africa and South America, you can see that the rocks line up as if this was a big cake, and you cut the cake down the center and pull off the Africa piece and the South America piece. The layers would have been matched up the same. Similarly happens in North America and North Africa, and then into the more northern lands as well. Looks like they were once together. The fossils present on each of these lands indicates that they must have once been together. There are several land reptiles that exist in both Africa and South America, and also some freshwater reptiles. It shows that these continents must have been together, because you couldn't have this freshwater reptile or these land reptiles, for example, appear in the same form in both South America and Africa if they were apart and not once together. One example here is a mesosaur. This is kind of like a little alligator type animal. You can see the fossil given here. This is one of the examples both in South America and Africa. Even plants give us indications of how these continents must have been together. Here is a Glossopteris leaf encased in amber, and you can see that this particular plant was pretty prominent across both South America and Africa, indicating that these were probably once together. Additionally, glacial evidence, glacial striations, or scrapings of glaciers show that on the southern parts of the continents, it makes sense that they were once together and the glaciers radiated out in all directions. We also see evidence of tropical deposits in areas we wouldn't typically see them. For example, in northern Canada, we see tropical deposits, indicating that when plugged into North Africa, North America was probably tipped on its side at one point, more so than it is now. But we do see tropical deposits, indications that show us that these lands were once together. So that brings us to the idea of plate tectonics. Continental drift took its form in the early 1900s, but really didn't gain steam until the mid 1900s, when more evidence was put together to help suggest that the continents were drifting and actually explain the mechanism of how they were drifting. In 1960, a retired military captain, Harry Hess, did quite a few studies on the ocean floor, particularly in the Atlantic Ocean. What he noted was that on maps of the ocean floor, and these maps were put together in the 30s and 40s to try to get a leg up in the World War II. So we had good extensive maps of the ocean floor. And what Harry Hess noted was that there was a volcanic mountain chain that went down the center of the Atlantic Ocean. He found that very curious, and he did some studies on it and on the rocks there. He found some very interesting things. The rocks get older as you get away from the ridge, and this actually suggested that perhaps these rocks are moving away from one another, that the ridge is a spreading center driving movement of plates apart. Harry Hess did some studies on the rocks along the mid-Atlantic ridge there, and he found that the rocks there, as not only do they get older as you get further away from them, but their magnetic signatures change in a concentric pattern on both sides of the ridge in stripes as you move away from the center. Very interestingly enough, he took a magnetometer across the ocean floor. It's a device used to check the magnetic signatures of rocks, and what he found was that the magnetic polarity of the rocks went normal, but then it switched to reverse polarity, suggesting that the Earth's magnetic field had changed over time. And so what he did find was that there were alternating stripes of crust of normal and reverse polarity on both sides of the mid-ocean ridge, and they were in concentric stripes, indicating that this thing was moving apart. So Harry Hess decided that these ocean plates are pushing apart from one another, and this is what's actually driving the movement for the plates. So he noted that the ocean bottom is about 3.7 kilometers deep, with two areas of exception: the continuous mountain ranges that were volcanic mountains, where Harry Hess thought that we had spreading centers, but also narrow trenches that extended to depths of more than 11 kilometers. What this suggested was that where the plates are actually coming together, that one plate will dive underneath the other, producing an effect that drags the head of the other plate down with it. And these are the deep places in the ocean, the deep ocean trenches. So this is compelling evidence to suggest that plates are spreading apart, and they're actually also coming together and diving into the mantle to recycle. Additional evidence that the plates were moving were provided with hotspots. If you take a look at Hawaii, for example, the Hawaiian Islands track back westward and then further northward, all the way back through the Midway Islands and the Emperor Seamounts, and all the way up to almost the Aleutian Islands of Alaska. And what this indicates is that the Pacific Plate has been moving atop a stationary hotspot coming from the mantle over the last 100 million years. As the Pacific Plate moves over this hotspot, new volcanoes are made and old ones move off to the side to make way for the new ones. And so hotspots and the tracks of these hotspots show that the plates are moving. Additional evidence gathered in the 60s showed that the earthquake epicenters actually map out the edges of these so-called lithospheric plates, that where we find the most earthquakes are where the boundaries of these tectonic plates lie. And so it was a very interesting discovery. If you look at the earthquake epicenters here from 1961 to 1967, you note that the earthquake epicenters have a pattern that indicates that they are part of the edges of tectonic plates. Also, if you look at the depth of earthquakes, you note that the shallow earthquakes are nearest the edges of the plates, and if you get further down to the deeper earthquakes, they actually move off to beyond the plate boundary. to explain this in a little further detail, what we see then is, for example, when we look around Japan, most of the earthquakes occur to the east of Japan in the ocean, where the Pacific plate is diving underneath the Eurasian plate over there, the Eurasian continent. But as you track the earthquake depth, you note that deeper earthquakes occur underneath Japan, and still deeper yet earthquakes occur underneath the Sea of Japan. This indicates that there is a tectonic plate diving down into the mantle at an angle, and the earthquakes show us the path of this plate. So it's pretty compelling to suggest that these plates are moving down underneath. And simply by using satellite and GPS, you can track the movement of these plates. Some of them move faster than your fingernails grow, but that's what we're talking about. We're talking about millimeters per year, but nonetheless, they can move at a pretty good clip. Some of the fastest moving plates are the ones that are spreading apart at the East Pacific Rise, which is just off the coast of South America there in the lower left of the map. All the evidence we just talked about then provided for the theory of plate tectonics, the explanation for all these scientific observables. The theory of plate tectonics was born in the 1960s once we saw all the evidence. The evidence abounded, the mechanisms for movement seemed plausible, and the explanation was developed and widely accepted. Thus, a theory was born. The theory of plate tectonics, though, continues to develop as we grow in our understanding. We get new data, our hypotheses are modified, the theory is altered to be more correct. Theories never claim to be 100% correct. They're only as good as the data that is involved in what they're explaining. But nonetheless, it's important to note that science is never static. It's a growing, evolving body of knowledge that creates an ever better understanding of how the Earth works. And theories provide explanations for how the Earth works. To summarize the theory of plate tectonics, it is that the lithosphere is divided into 12 distinct segments or tectonic plates of lithosphere that move over the asthenosphere, the partially molten area of the upper mantle. The plates can be continental crust, oceanic crust, or both, and the study of the movement and interaction of these plates is called plate tectonics. You can see in this picture here, we have the North American plate, which has both continental crust and ocean crust on it. We have the Eurasian plate, the Pacific plate there, the Australian plate, the African plate, South American plate, and of course lots of other little subplates that end up causing lots of geologic action on the Earth's surface. The driving force for plate tectonics? Essentially, these lithospheric plates are sliding atop a partially molten asthenosphere on convection currents. Believe it or not, the rock moves in the upper mantle. It's so highly under pressure and so superheated that it actually has a motion, and it allows for gliding and moving of the lithospheric plates. Subducting slabs are pulled downward by gravity, and so that's also helping to drive the motion. There's an enormous amount of upward magma pressure at these spreading centers at the mid-ocean ridges. You see in the center of the picture here. The mid-ocean ridge buckles upward, and then gravity drags it downward, and the two slabs pull apart from one another. This then, in concert, is the driving force for plate tectonics. Let's talk then about the plate boundaries. This is where all the geologic action on the Earth's surface takes place. The zone of plate interactions come in three varieties: either divergent plate boundaries, which is where the plates pull apart; convergent boundaries, where the plates collide with one another and come together; and transform plate boundaries, where they slide past one another. Each in their own right makes for earthquakes, volcanoes, and mountain building in various ways. If we take a look at a diagram of how this might work, we see that there are spreading centers in the center of the ocean there. Actually, also, those spreading centers do take their origin and sometimes in the centers of continents that you see in the lower right there, or on the right side of the diagram. Those would be your divergent plate boundaries. Where the plates are coming together, where you see the two arrows coming together, you see it labeled there subducting plate. They call it, when one plate dives underneath another, they call it subduction. When this takes place, waterlogged ocean crust melts very easily, and it's charged with water vapor, so it's very buoyant. It rises and burns its way to the surface to form volcanic activity. So wherever you have a subduction zone, you're going to have volcanic activity, either along the coastline there, on the right side of the diagram, where we see the mountain chains, or on the islands that we see on the left side of the diagram there. Either way, volcanoes occur at subduction zones. There are isolated hot spots as well that you see pictured there in the diagram, where a single plume of magma will reach the Earth's surface and cause a chain of islands as the plate moves over top it. We see here the Pacific plate in the real-world context, where we see the East Pacific rise in the lower right, shoving the Pacific plates to the upper left of the screen, causing subduction zones all along the area of the Aleutian Islands, along Japan, the Philippines, and down through New Guinea, near Australia there, and New Zealand. All those areas are subduction zones and causing major earthquakes and volcanoes. And there are even some transform motions there where we see labeled on the upper right the San Andreas Fault and the Queen Charlotte Fault there, and the Alpine Fault in the lower left. We'll start talking about divergent plate boundaries. This is where two plates move away from each other. What happens is, as these plates move away, the upward magma pressure causes them to slide apart from one another, and there's a gap in between them called a rift. This rift fills with molten rock from the asthenosphere. It's very dense magma. It's very runny. It's not explosive. It freezes really in place. It just oozes out and freezes in place to create new crust. So the youngest rocks on Earth are found right nearest these rifts where they're spreading apart. And of course, the rocks get older as you move away from the center. The whole suite is called a mid-ocean ridge, and an example would be the Mid-Atlantic Ridge. The Mid-Atlantic Ridge had its origins by basically unzipping Africa from South America and North America from North Africa. And that occurs from continental rifting. What happens is that upward magma pressure builds up for whatever reason in the mantle. That's a topic for the geophysics class that we might take someday, but for right now we just note that for some reason plates build up heat energy underneath them, and that upward magma pressure drives the plates upward, and when it does so, it cracks the crust and allows new crust to ooze up and fill the gap there. That new crust that's formed is very dense and very thin because it's coming directly from the mantle. And because it's dense and thin, it sinks down into the asthenosphere and creates low places of the Earth where it fills up with water. So as you can see by letter C in the picture, it's starting to fill up with water. We have a shallow sea, and then eventually in the last picture there on the bottom, we see the ocean crust, which is the thin, dense crust situated there where we have spreading centers and we've got an ocean developing. This is how we think an Atlantic Ocean would form. An example of where we could see the Mid-Atlantic Ridge on the surface is in Iceland. The North American plate is on one side of Iceland, the Eurasian plate on the east side of Iceland, and the Mid-Atlantic Ridge you can actually see will go right through the center. It's a drop-down area where we can see basaltic-style magma. Of course, Iceland in the north there is one area along the Mid-Atlantic Ridge where we've had an extra amount of magma pour out onto the Earth's surface. Rifting is taking place in the East African Valley. The East African Rift Valley is a place where continental rifting is driving the Horn of Africa away from Africa. The Red Sea is also actually part of this suite, and the Red Sea is parting, as you can see pictured in the arrows there. It's a divergent plate boundary, and so too is what we would find all along the East African Rift Valley there. Convergent plate boundaries are where two plates collide. Because of the motion of these plates coming together, you can have ocean crust or continental crust or both coming together. So there are three types: either the oceanic convergence, in this case the older, denser, more waterlogged plate subducts underneath the other. You can see that pictured in the lower left. Oceanic continental convergences, where the ocean plate meets a continental plate. The ocean plate always subducts under the continental plate because the continental crust is made of very low density, very buoyant rock, and so the ocean crust, being more dense and waterlogged, always subducts underneath. pictured in the center there. And continental-continental convergence is where two continental crust pieces come together. In this case, we create a land crash where neither continental crust pieces want to go down into the mantle, and so they crumple up into a mountain chain and form mountains. So this is our three types of convergent plate boundaries. First, to detail the oceanic-oceanic convergence, when the lithosphere descends down into the mantle, it of course melts to produce volcanoes, and eventually they pop up above the ocean surface to form islands. Japan is a good example of this. Off the coast of where the subduction takes place is a deep ocean trench where one plate is dragging another underneath it, causing the head of the plate that's not being subducted to get dragged down and a deep place in the ocean. And then, of course, we have the arc of islands just beyond that point. Let's take a look at Japan. Japan is the result of the Pacific plate diving underneath the Eurasian plate there, as you see pictured in the upper left. The lower left shows that Japan has a bunch of volcanoes all around it because of this. All the little red triangles there indicate that. As the Pacific plate and the Philippine plate dive underneath the Eurasian plate, these volcanoes form the island chain of Japan. An oceanic continental convergence is where the denser ocean plate subducts under the continental plate. And when that happens, again, we have crustal melting. When crust has a lot of water in it, it has a tendency to melt quickly and produce a buoyancy that forces that crust or that magma to the surface to erupt to form volcanic mountains on the edge of the continents. It again produces a deep ocean trench. The Andes Mountains are an example of this. The Andes Mountains are the result of volcanism that takes place because the East Pacific rise off the coast of South America is shoving the Nazca plate underneath the South American plate, producing the Andean mountain front. Now, in addition to those deep ocean trenches and volcanic mountains, you also get some massive earthquakes with this because when convergent plate boundaries take place, there's a lot of pressure. A continental-continental convergence is where two plates crumple up and form mountain ranges. It's essentially, this is a big land crash. Neither piece of continental crust will want to subduct. The one that perhaps was attached to some ancient ocean crust might have been subducting to begin with, but then begins to crumple up the other continental plate. This produces a high mountain range, and oftentimes it buckles up the continent behind it to produce high plateau. The Himalayas are a great example of this. The Himalayan mountains were produced and are being produced because India is smashing into Eurasian plate. The Indian plate here has brought India toward Asia for the last 70 million years, and then for the last 10 million years, India has been crashing into Asia. As a result, the Himalayan mountains have buckled up. The Tibetan Plateau, just to the north of the Himalayas, is an area of crust that's also upthrust because of the major land crash taking place there. And all that mid-continent Chinese buckling there is what causes some of those really deadly earthquakes that we see occur in China, and we have seen in the past occur in China. Those highly populated river valleys are also in a dangerous tectonic area. Transform plate boundaries are where two plates slide past each other horizontally, either in opposite directions or in the same direction, just at different speeds. Our archetypical example here is the San Andreas Fault in California. There's also another fault called the North Anatolian Fault System, and this one runs through the north of Turkey. The San Andreas Fault oftentimes has lowered areas where it actually does move with respect to one another. The two plates, the North American plate and the Pacific plate, slide past one another, making the Pacific plate move in a northwestward motion and the North American plate moving relatively in a southeastward motion, causing movement and breakage and shifting all along that front. And of course, San Francisco is one of the main areas in that along that fault line. Turkey is kind of like the San Andreas Fault on its side. Through the north of Turkey, there's a large fault system called the North Anatolian Fault System, consistently producing magnitude 7 earthquakes as the transform motion slides the north of Turkey one way and the rest of Turkey the other. Our last tectonic environment would be then hotspots. Hotspots are isolated pockets of magma that erupt at the surface as the plate moves over the top of them. Hawaii and yet the Yellowstone National Park are two great examples of this. As a Pacific plate moves over the top of Hawaii, or moves over the top of the hotspot that feeds the volcanoes of Hawaii, you can see the Pacific plate move over the top of the hotspot, producing a volcanic chain. Of course, the large island of Hawaii is under the hotspot right now. Kilauea and Mauna Loa are two vents that the volcano has taken over the course of its existence, and Loihi is forming in the ocean just to the southeast. It will be the new island of Hawaii. National Park is also a example of a hotspot. Yellowstone has a large magma chamber under it that causes all the heated groundwater and geyser activity. There's many earthquakes that occur along the top of that caldera that indicate that the magma pocket is surging and shifting. The Yellowstone caldera itself is about 26 miles wide. It's a very, very large volcano. We call it a supervolcano. Yellowstone is actually tracked north and eastward over time. For the last 20 million years, Yellowstone has been erupting about every 600,000 years as it tracks north and eastward. It's now currently in northwestern Wyoming. It does indicate, though, that the plates are moving and is an interesting byproduct of plate tectonics. That's a look at plate tectonics, a real fundamental concept in geology. I'm glad to have talked to you about it because it really sets up a good discussion on earthquakes and volcanoes for us, which we'll be discussing in the upcoming weeks. So thank you very much for listening, and I look forward to talking to you soon.